All right, and now we really are ready to start doing some calculus, some real calculus work into any of our on any of our parametric curve. Okay, and so this lesson here, even though supposedly a continuation of the video lesson that was previously delivered on parametric equations, but this lesson itself can also be an independent lesson for anyone who already had some background with parametric equations and ready to really start applying the calculus work on top of that and really do the calculus work on top of that. And so for that reason now I will go ahead and restart my example numbers so that this lesson can also be treated as an independent lesson on its own. Okay, so that's all I need to say before we really start. Okay, but now, so at this point, anyone arriving at this video here already knew what a parametric, what a set of parametric equations is. And so at this point, summarizing the ideas we have seen in my lecture on parametric equations, then now any curve in the x and y plane is a accumulation of all these points right here. So it's a trace of all these points right here. So any of these points, we can think of that as a position. If we have a particle that's moving on this point right here, on this path, this curve right here, then each point here on the curve is a position. And so x and y is the coordinates of where the current position of the particle. But now we have already learned that x coordinates can be expressed as a function, and that's as a function x of t. And so t now at this point, even though most of the time in my video lecture in parametric equations I try to avoid using the word time because the parameter t can represent a lot more than just time, but now we can start allowing ourselves to start treating the t parameter here as a time parameter. And so back to what I was in the middle of saying, then the x coordinates at any point, at any position of our particle on this curve here can be expressed parametrically as a function x of t. So t is a parameter, and now think of that as a time parameter. So the same will happen with the y coordinates, and any point, any position on this curve here, or back in the video lecture for parametric equations, then I call any of this curve here a path as well. Okay, and so y, the coordinates of any points the y coordinates of any position can also be regarded as a function y of t. And so we have seen all this idea. There's no need to restart any of that. Okay, but so now, so just for viewers and for my audience, my students to also be aware that so a curve like this can now be represented parametrically. So the curve that way, a path that way, is now sometimes people also refer to this as a parametric. Okay, a curve on the x and y plane that can be represented by a pair of parametric equations. We refer to that curve as a parametric curve. Okay, so that's just another terminology to introduce when we start learning about parametric equations, then the term parametric curve doesn't happen too much. But then as we start bringing in calculus into our work with parametric equations, then the term parametric curves will start being used a lot. Okay, and so now that's all I need to recall from the earlier lecture on parametric equations. And so now this is the kind of calculus work we can do. So I just need to roll back to the point where we have defined x as a function. Just only think of x as a function in terms of t. Okay, and also think of y as a function, y in terms of t. Okay, and so for short, just x of t is good enough, or y of t is good enough for any viewer to understand that, hey, x here is a function of t, and y here is a function of t as well. And these two functions are just any two functions. They are not necessarily related. Okay, even though in my lectures for parametric equations, I've tried to, I also explained that they can be related if we know how to make that relationship come out, where we so-called the Cartesian equation. But here again, let's roll back to the point that we don't need to worry whether these two variables x and y are related or not. They're just, x is one variable, but it is a function in terms of t on its own. Y is another variable as a function in terms of t on its own. And so now if we're having two completely separate functions, x of t and y of t like this, then, and of course, I'm not even going to give out anything, any actual function like, is that a t squared plus 1, or is that a cosine of t, or is this a e to the t, or whatsoever. That's not even what we need to worry right now. But now, as long as we can have a function, a function of some kind, then with our calculus understanding, then we can find dx dt, okay? Or to be precise, the arrow notation is probably a little bit hard to understand for the student at calculus level, beginning calculus level. So how about differentiate that function, take the derivative of our function in terms of t, then that gives us, generally speaking, dx dt. And this is where our calculus understanding is coming in right there, okay? And so same way, we can do the same thing. I'm just saying that with any function, then we now can take the derivative in terms of the main variable. So here, each one of our x and y variable is a function of t. So now t is the main variable, the independence variable. So we can take the derivative, differentiate this. Look at that, the operator again. I'm using that same operator we've been learning throughout all of those video lectures for calculus. And so I can also take a derivative. I can take the derivative for the y function in respect to t like that. So differentiating y in terms of t. And so of course, consequently, we will end up with a dy dt. Okay, that's a dy dt. Okay, and so now I have to admit, even though I love to give out as much details as I can, but my viewers for this video lesson here are supposedly beginning calculus students. So believe me, in my teaching experience, when students arrive at this beginning calculus course right here, then only 30 to 40% of them have some physics background, some physics course before calculus. Only 30 or 40%, so not too many. So a bigger majority still do not know much about physics, especially vectors. And so it's really hard for me to explain what's the direct meaning, what's a further impact of these, the direct meaning of dx dt and dy dt together, for a particle moving on a curve. But anytime that you arrive at your Calculus 3 course, then you can go ahead and come back to my channel here and view my other lessons that will connect directly with this. And there I will be able to explain there. And I mean, after you have already had some physics course and go through a few more courses in calculus, and when you arrive at Calc 3s, somewhere there where you have more understanding, then you will be seeing another lesson of mine where I deliver the material as for targeting the Calculus 3 level students. Then there I will be able to explain better details about how dx dt and dy dt together can be understood as you know, as some important role for a particle that's moving on a curve like this. But at least this is what we can still do. Even though it sounds like you gotta wait until some future course to fully understand what dx dt and dy dt together are doing to a point, or representing to a point. But at least up to this point, we can still understand one thing. So see, now if we think about a path right here, then think about I'm tracing my pencil tip along this path, and that's what we should be familiar with by the time that we finish learning about parametric equations. Then when we think about there's a particle being in motion on this curve, on this path right here, and at any instance there will always be what's so-called a horizontal, a horizontal left or right motion. Okay, so see, go this way, or you can go back this way, you can go that way, you can go back this way, and that's called a horizontal motion. So observe the motion of the particle on this. See, now I'm heading to the left, and yes, now heading up. So don't worry about the up yet, because I didn't talk about that yet. But at least I'm little bit turning back to the right. So there's a little bit of right hand side motion, and then there was mostly the motion that heading to the left. So there's horizontal. So my bottom line, my point here at the bottom line is there's the horizontal motion. Okay, and so if there's horizontal motion existing any point at any instant when the particle is moving, then that motion there, we can represent the rate of change, the speed there, the horizontal velocity. The physicists call that the velocity. This is can be understood as the horizontal, okay, velocity. Even though I'm trying to only deliver in a very limited, assuming that you have a very limited background in motion in two-dimensional planes. That's why, as I said earlier, you need to go through a beginning physics course, and then somewhere in your courses, when you arrive at Cal 3, like that, then you will understand much better about horizontal velocity. But at least now I can describe that when you make motions on a plane, then you can go left or right. You go left or right. Your motion can be left or right, and so left or right generally can be regarded as horizontal motion. And so the dx dt here represents, because the x variable is what we traditionally represented the value that happens on that are being arranged on the horizontal axis. And so changing in x coordinates over time. So now let's say we're going to start using more intensively the t variable here for time, the t parameter here for time. Then changing in x over time, that means how fast we change on the horizontal axis here over time. And then, so now, once we understand now that dx dt can be regarded as the horizontal velocity, then the dy dt, same way, any particle, see, if you observe my pencil tip motion closely earlier, then you can see that left and right is not the only thing that's being part of the motion of my particle here. As my particle, see, it was from down here, and then eventually it went up here. And so left and right, but then together with some up and down, that's how it can go left and right, but up and down, okay? So there's a vertical motion as well. So any movement, any particle moving, doesn't matter how crazy the path is, but there has to be the left and right and up and down motions together, and that's why we got all different kinds of directions coming out of that. And so again, all of that will become so clear when you actually start getting yourself enrolled into a physics course where they will introduce the concept of vectors. It's just sadly that vectors are not being introduced at Calculus 1, and that's why it's very limited tools. I mean, I have a very limited amount of tools to deliver for my audience, supposedly being at Calculus 1 the level. Okay, but we can just take what we have and try to have some understanding of what we have right here. Okay, and so now my bottom line for so much explanation so far, this dy dt now is to represent the vertical, okay, so because there's vertical motion, so of course there will be vertical velocity. Think of that as just how fast instantaneously the particle is moving, how fast the changing vertical in the vertical coordinates, right, is happening. That's what the dy dt is. Okay, so that's vertical velocity, that's what dy dt is for, and horizontal velocity that's what the dx dt is for. And so we don't have to do that kind of problem yet in our in our calculus course here, but in reality out there, in practical situation out there, anytime you have a point moving on a plane right here, a point moving on a particle that's moving on a path, on a curve, then dx dt and dy dt always exist together. Okay, you cannot only have this dx dt and completely having dy dt absent. It makes no sense that way. It's just the way how life is. And math is just one way we study how we're trying to describe how life is out there. Okay, so and so same way you can never have dy dt without having a dx dt. So dy dt and dx dt always exist together. Okay, and so now dy dt is a vertical velocity. Dx dt is a horizontal velocity. But now, just think about, and so when I'm talking about, now when I'm using the term horizontal or vertical, up and down or left and right, then viewers will start understanding that it has some, behind the scenes, it has some direction being involved. Okay, it has some direction being involved. But now there's a term that we are introduced to since we are kids. Speed. Okay, so speed is also how fast you go. But you see the major difference between speed now is that speed is completely without the directions. So velocity is the speed but with direction. So either you go this way or you go that way, and how fast you go. So how fast you go truly is speed. How much distance you make over time, that's speed. But now there's directions being involved. That's why it becomes a velocity. And again, all of that will become so clear when you go to physics and start the learning about vectors and all that. Okay, but here, just think about when you're on a path and you can move on that path. You can move fast on some portion of the path, and then you move slower, but you still stay on that path. And then you go faster and then slow down. Okay, and so in that way, completely ignoring the direction where your curve is crazy turning and all that, then we're still going to have how fast our particle is moving, and that's called the speed vector. And so now speed is now, again, as I'm introducing here, it is very limited for me to explain because I understand my viewers don't have all that. Most of my viewers, a bigger majority of my viewers do not have the physics background yet when you're viewing this video. But so now I can show you how speed is related with these two quantities, and then remind yourself to bring this to your physics class or your Calculus 3 instructor and ask why speed is being given as this formula, and you will get all of that explanations. Okay, but so now speed is simply just the square root of the horizontal, the square root of dx dt squared. Okay, the horizontal velocity squared as quantity plus dy dt squared. So dx dt squared plus dy dt squared inside of the square root. This is the calculation that gives us speed. Okay, because now think about it, the consequence of, I mean, we don't even need numbers to plug in or anything like that, but right here looking at this formula, then the answer that comes out from this formula will always be a positive value. Because why is that? It's just speed. It's just speed. We just only measuring how much distance we made over time. Okay, and that's the reason why speed will always be positive. Whereas, see, be careful with the dx dt and dy dt here. If we set the direction to be going to the right hand side here as the positive direction, then sometimes dx dt can be negative due to the fact that we have a rate of change, we have a speed that's going, but in the opposite side right there. Okay, so dx dt and all these dy dt, these velocities, they can have negative signs in it, but speed will always be positive. Okay, so definitely check out my video for Calc 3 level when you are there, when you're at the Calc 3 class, to have to again see how I explain. But assuming you already had all that background, so that this explanation can become a much more clear explanation. Right now, of course, forgive me that I have to assume that my viewers here have limited understanding of motions, and especially a bigger majority of students or viewing this video without some physics background right there. Okay, and so but with these three understandings so far, we can build a lot of problems already. Okay, so now let me turn over to my computer screen right here. And let's look at our first example. Okay. And so now, example 1 here says the position of an object. Okay, so I keep using the term particle, but here it could be an object like a big rock that you throw into the air, or you throw on a floor and it rolls into some kind of path like that. So the position of an object in the xy plane relative to the origin. This is just optional information right here, with the distance measured in meters. Okay, so now we know that we're in metric system. So the position of an object in the xy plane at time t seconds is given by the parametric equations. Okay, so x of t equals t squared minus 4t plus 1, and y of t equals t squared plus 2. So I am going to highlight this information because that's our system of parametric equation. And that's, in other words, together, these two equations together make up our parametric, what's so-called parametric curve. Okay, that I introduced that term earlier. And so now, question part A in our example here. Find the object's horizontal velocity at t equals 4. Okay, and so all of that reason why I spent so much time trying to explain, and hopefully the viewer will catch my understanding. But see, now when the problem is looking for directly in words horizontal velocity of the object, that means we are now looking for dx dt. Okay, and then let's one more time look at the wording of the problem here. Let's find the object's horizontal velocity at the given time t equals 4 here. So that means this is how we are going to answer our question in part A. So now we know, and allow me to copy down the two equations that I highlighted, the two parametric equations. So x of t equals t squared minus 4t plus 1, and our y of t, our position in terms of t, is t squared plus 2. Okay, and so now the question is looking for find the object's horizontal velocity at t equals 4. So that term horizontal velocity right here is exactly what I have just now explained before we turn into the actual problem. Now we're looking for dx dt. So before we can actually find the velocity, the horizontal velocity at t equals 1, then we have to find the general dx dt, which is the general instantaneous of this point. Because you see, ever since we learned about calculus and in other video lessons, in earlier video lessons, I have explained hopefully in details enough that now any of our rates here, velocity is a rate, is the way how we understand rate when there's motion. Okay, and there are other kinds of rate of change, but any of these rate here is an instantaneous rate of change. Okay, and so that's why at the instance when t equals 1, how fast is the particle, is the object moving on the horizontal axis right here in respect to the horizontal axis. That's another way of saying it. Okay, but so now in order to do that, we have to find the derivative of our function x of t. So this is just, in other words, asking for x prime right here. So dx dt or x prime is now going to be easily 2t, and that's where I said this is where we really apply our calculus understanding. So now easily we get 2t minus 4. That's my dx dt. Okay, and so now the question is asking for, so this is the general formula that regulates the horizontal, the instantaneous, the general instantaneous horizontal velocity at any time instant. But now particularly at t equals 1 right here. That's what the question was looking for. And actually, I mean t equals 4, not 1. And so now I'm going to switch that to t equals 4. And I apologize if I accidentally said 1 a couple times before. But so now at t equals 4, then the velocity we're looking for is just simply the dx dt, but substituting in t equals 4. Okay, and then I also have introduced this symbol here, that which means from where our currently found derivative, general derivative, which is simply gonna, this symbol is an evaluating symbol, evaluation symbol. We're evaluating t equals 4 into this formula. So, or that means plug in for simplicity. And so 2 times 4 minus 4. Okay, so our velocity, our instantaneous velocity right at that instance when time hits t equals 4, then we have the instantaneous velocity, the horizontal instantaneous velocity is being positive 4. It's a positive. Okay, then that means the curve could be going, you know, crazy up and down and waving left and right and up and down and all that, but you know, at that instance in particular, at that instance t equals 4, then the particle was, you know, horizontally, the particle is moving at positive 4. Now you see, now the problem told us to work with distance in measures, in meters right here, and time is in seconds. So that means here our units here is, our particle is moving 4 meters per second. Okay, and positive means it's heading that way at that instant. It's heading to the right hand side at that instant. Okay, and so now in that way, let's advance over to our problem B of the example. Okay, so question B of the example. So same exact problem right here. So that means all that wording, all that description of the curve is here. We got the x of t and you got the y of t, nothing changed. The question now is only, the only question here is find the object's vertical velocity at time t equals 4. So now we're looking for vertical velocity at given time t equals 4. All right, so here we go. So I highlighted that term, the velocity, vertical velocity here, because just now again I was explaining vertical velocity is where we're gonna need to find dy dt, because y of t is responsible for the vertical coordinates of any position of our point. So when our particle is in motion, then there's, see, left and right and up and down, it's one, see, left and right, and then gradually rising up right here. So there has always been, you know, left, right, and up, down together, always existing together. That's how, you know, that's how particles that live in the 2D world make motion. Okay, and then when we later on when we learned about motion that can be taking place in the 3D world, and then it's gonna be, you know, another axis that's going along, but that's gonna be a long story from now. So now what I need here at the bottom line is a dy dt. Okay, and so dy dt comes out easily to be, first term gives me a 2t, that term being a constant, so taking the derivative is a 0. So my dy dt, my general instantaneous rate of change, my general instantaneous velocity up and down here is a 2t. Okay, and depending on whichever time that is, our vertical velocity is a 2t. And so now at time t equals 4, this is what we are going to get right here. 2 times 4, or formally speaking, I shouldn't skip this, dy dt evaluated at t equals 4, that is going to give me 2 times 4. Okay, so my final answer here is going to be positive 8. So allow me to highlight, when it gets into motion, then we got to be clear about which direction that is. So positive, now up and down here, so if we assume up is the positive side, then our motion here is moving, the calculation came out positive 8 meters per second. So that means at that instance, our particle was moving upwards, right, at the rate 8 meters per second. Okay, and so that's what it is. We have so far answered 2 questions in our example 1 right here. And so in the end, it doesn't look so bad. With our limited understanding so far, and believe me, I have not explained to all my fullest understanding yet, because again, I have to apologize that that allow me to assume majority of my viewers here in this lesson is viewing it without much understanding of physics. So it's not possible for me to introduce those concepts from physics to bring in here, because that brings nothing good. Okay, but if you can find my other videos on the same and the similar topic here, parametric equations again, but in a Cal 3 level, then there I will be able to explain this in a much even a much more detailed settings there. Okay, so now that's the answer for our question in part B. So let's now look at the question in part C right here. Let's see what it asks. Okay, so there we go. The exact same wording right there. The position of that object and being described by our two equations, x of t and y of t right here. The question is ultimately looking for find the speed of the object at time t equals 4. All right, so now pretty straightforward. Recall again, and now let me move on to the other board right there. Speed. We learned this formula regarding speed. It's the square root of dx dt square plus dy dt square. Okay, and so now in this particular problem, we have already found the x dt in our preceding step. Sadly, I also erased that on my other board, but I can still remember that here. So speed here as a general setup for here, we're looking at the formula, I mean square root of 2t, and now inside of that square root 2t minus 4 in parentheses square, and then we have another square here plus 2t all square. Okay. And so that's what it is. And so at this point, you can quickly use some algebra to FOIL out your perfect square right here and combine like terms with all that. Okay, to come up with a reduced of algebra expression before we start evaluating. Or we can just, because in the end at time at t equals 4 right here, what I was saying earlier, we can just directly, as well as another option, we can just directly substitute this value into our variable t in this expression, and that gives us our speed, our instantaneous speed on the path right there at that particular instant when t equals 4. Okay, so allow me to go with the way that without simplification, because I understand a lot of the time, very understandable that the students and viewers in general, they don't want to do too much algebra. So without doing too much algebra here, we can just directly substitute that in. So at t equals 4, speed will equal the square root, and now t being substituted in. So 2 times 4 minus 4, all that there in parentheses, square, plus 2 times 4. See, every t is being substituted by 4, all square. Okay, and so now I am going to take about a minute or so for my calculation, and I should be able to write the answer on the other board. All right, so now on my other board right here, so that square root right there is the same as speed there. After doing the math, we're looking at, it's a square root of 80. Okay, all right, and we don't really need to simplify this square root expression. So the final units here is meters per second. Okay, but speed will always come out being a positive quantity. Okay. And now let me also explain a different way how we can apply. So example 1 we did right there was one way how we can apply calculus, taking the derivatives directly into the parametric curve right there and understanding the x dt as the horizontal velocity and the dy dt as the vertical velocity, and together with the horizontal and vertical velocities, we can come up with the speed. And so that was the entire example 1 was all about. And so throughout the entire example 1, we never had to worry about whether x position and y position are being related. Okay? But now the different way to apply calculus that I have mentioned earlier now is this. So think about now, what if we got a curve. Any curve on the xy plane is a curve. So what if our curve here, okay, every point here is a pair of value x and y. You gotta agree with that. Okay, any point on this curve gotta be a pair of x and y. But now what if we have to see this curve here as an equation relating, how about y equals a function of x? That's one way to see that. It's an equation relating x and y. Or what if we have to see this curve, because remember back in that video lesson on specifically for you to get to know about parametric equations, then there was that kind of problem where we got to be able to convert from parametric curve, convert parametric equations into a Cartesian equation. This is an example of a Cartesian equation, ladies and gentlemen. It's an equation that only relates between x and y, even though I use that friendly functional notation. So in another way of seeing, you can also see the relationship between x and y as x is a function of y. Okay? So I'm saying now that in the situations, and those situations will come, in the situations where x and y are related through a functional relationship like this. Okay? So y is a function of x, or in the other case right there, or in the other scenario around, x is a function of y. Okay? So then if that case happens, and here how we can see the calculus. Now, but still recall that now each one of the x itself is already a function of x of t. It's just now I'm talking about in a situation that where we already recognize a relationship between x and y. X and y are related. We now know that. But before we know that, we still knew that x is a function of t and y is a function of t. Okay? So now, ladies and gentlemen, if x and y are related as a functional relationship, y equals f of x like this, but keep in mind, keep in the back of your mind that y is a function of t already, and x is a function of t already. Okay, and whether we know it or not, whether we know x of t or y of t explicitly or not, that's not important. But this is what I'm doing. Assume we just know that it's a sum function, but completely implicit for us. Then this is what I can do. Okay, I am going to, from where our y is a function of t. So I am going to differentiate y in terms of t on the left hand side. And the right hand side, I am going to also differentiate in terms of t. Now take a moment and take a deep breath to recall yourself where you have seen this concept. Okay, so have tried to remember to some far back to memory. This is the concept of the related rates, how we derived the related rates. Right there. So now we just know that our two variables x and y here are related with each other. And so now and t is of course out of nowhere. T is not directly involved in this equation anymore. But thinking of each one of x and y here as a function of t already, then we can directly differentiate both sides in terms of t. Okay? And so now carrying on from that idea right there, now on my next board, then the left hand side simply just give me dy dt. But wait a minute, isn't this on the left hand side the vertical motion of our particle if the particle is moving on the curve that came out from the functional relationship between x and y? Okay, because in the end, even though it's a graph of a function, but it's a curve, it's a path as well. So any point moving on this curve has up and down motion and left and right motion. Okay, horizontal motion and vertical motion. Okay, so dx dt on the left hand side should equals, now let's do a quick little bit of scratch work here, d dt of the f of x. Let's try to find out what that is. Okay, this function here outside is some f function. Outside is some f function. And then inside of that, there's x, but see, at this point, it would be a little bit more beneficial to think of the x here as x of t right here. So there's the outside being the f function. We also don't know the f function. We just, outside is some function. And inside is our implicit function x of t. Okay? And so now when we take that derivative in terms of t right here, the chain rule now says we have to first take the derivative of the outside, which gives me f prime. But f prime of what? F prime of x. Okay? Because when we take the derivative and when we follow through the chain rule, then taking the derivative of the outside, we have to leave the inside arguments exactly the same way. And then the chain rule says we are going to multiply with the derivative of the inside, which is now, generally speaking, the dx dt that we're looking at. Okay? And so now this is what I recognize. This is the vertical velocity. Okay, this is the dx dt right there. This is the velocity, the vertical velocity of our point. This is the horizontal velocity, and this is just our, another way of understanding it, this is just our famous dy dx. And so another way of writing this equation currently, we got three different rates right here. They're all being related. We got dy dt is equals to dy dx multiplied with the dx dt. Okay. These are all three different rates that are related. Okay, and I highly recommend not to think of this as fraction, so you can cancel the dx with the dx here. It's not like that yet. Okay, it's not that yet, because so now dy dx is one symbol that represents the derivative of the outside function here, and the dx dt is the derivative of the inside function, which is now just our horizontal velocity of that particle moving on the graph of a functional relationship. Okay, and then the dy dt is, on the other hand, the vertical velocity. So either you can understanding that way, or seeing that as a dy dt equals dy dx times the dx dt. So more importantly, that comes out for us. Dy dx, I can divide both sides by dx dt here. So now I come up with a different formula. Dy dt over dx dt. Okay, and this is the formula where you will see that throughout a lot of standard calculus textbook. But again, in my teaching approach, in my teaching style, I'm a little bit against making my students to memorize. So I don't recommend at all to memorize this. As you understand the concept enough, eventually you will be able to derive this on your own. So stick with the related rates concept. Okay, and so here we came out with this simply because we put ourselves in a situation where y is a function of x. Okay, so if I said so, we came to all that there on the other board by putting ourselves in the situation where y is a function of x. But sometime, what if we are in the other situation? What if we are in the other situation, the situation where x is some function? Let's name it g, some function of y here. What if our relationship, it is another relationship between x and y, still a functional relationship, but x is a function of y here. Okay, so what if we're in that situation? Then still, each one of the x and y here can be on its own, a function of t. X is a function of t, y is a function of t. And so in that way, again, I see no variable t being involved here, but we can now go ahead and get straight into the problem, differentiate the left-hand side in respect to t, and differentiate the right-hand side as a function g of y over here, directly in terms of t. Okay, and so all this work here in my next step, then the left-hand side simply gives me dx dt. And the right-hand side, according to the chain rule, outside is a g of y function. So now taking the derivative, it's give me g prime of y. And the chain rule says we're going to multiply with the derivative of the inside dy dt. Because look at our function g again. The outside function is a g function, some g function. We don't even have to know what that is. But the variable itself, the variable y itself, is another function of t. So there's the outside and there's the inside right there. Okay? And so that's why this came straight out as a chain rule over here. But then we recognize, again, very similar to how we made our argument in the other situation, then this is right here, this the same as this is dx dy. Okay? Even though I wrote dx dt. So this is dx dy. And then multiply with that dy dt, and on the left hand side it all equals out to dx dt. Okay, and so in that way, yes, if our equation, if our curve was a curve that represents a function x in terms of y, then we also will arrive at another formula as well that you might also see quite a few times, quite often in many standard calculus textbooks out there. See, dividing both sides by the dy dt here. Then we can solve for dx dy. See, the correspondence here is that our function is x in terms of y variable. So that's why we can easily calculate dy dx if x and y are all parametrically defined. Okay, and so now that gives me dx dt over dy dt. All right, so that's another formula. But again, I wrote it down, I put it in a box like this, but I don't recommend my students, my viewers to memorize this. It's so much. Stay with the related rates concept right here. Just see how often I work through my related rates equation, and that will unlock all of your work. You can save yourself from memorizing too much stuff right there. Okay? And so now, enough with all that theoretical explanation here. Okay, so let's get into an actual problem so that you will understand why we have to do things like that. Okay, so now I am going to bring everyone into example 2 of our problem, of our lecture here, lesson here. So let's look at example 2 right here. Example 2 say let x, so there is a curve, there's a parametric curve right here, let x of t equals t cubed plus 2t, and y of t equals t squared plus 7t. So what we have here as given information, a pair of parametric equations. Okay, and so, and it's called a parametric curve because together I don't even have to see the graph, but it will give us some kind of curve. So question A right here is immediately asking, find the slope of the tangent line. Find the slope of the tangent line to the parametric curve at t equals 1. Okay, and complete the equation of the tangent line. Complete the equation of the tangent line. Okay, and so now a lot of things going on here. So let's break it down one by one right there. All right, so let's now start with that first part. Find the slope of the tangent line, the tangent to the parametric curve here. So this is why I had to spend some time introducing how the dx dt and the dy dt related to the dy dx or the dx dy, for example. Because here, now when we actually see our curve is obviously, apparently, or clearly parametric. Every position here is being explained by a t parameter. So a t parameter, a t value, the time parameter is responsible for changing of the position, okay, on this curve right there. But then in the end, for people who are seeing this, pretend that this is, I mean, we put ourselves into the situation that this is entirely a geometry problem. Okay, it's just you got a curve, okay, and it's a geometry problem. So yes, the curve might not even be the curve for a function. It's just whatever curve. But now at any point on the curve, there can still be a tangent line, as long as your curve is bent. You can have a tangent line. There will be a line at some point. At any point, there will be a line that just barely touches the graph at one point, and then immediately departs from the graph from that point, from that instance. Okay. So anywhere on the curve, either the curve is bent this way, bent like that, there's a curve. Even the vertical tangent line like that. And so because of that, we want to still find, and in the end, being tangent line, that tangent line here, tangent line there, there are tangent line, and there are lines. So lines have to have that relationship, either y equals mx plus b, right? That's in slope and intercept form, or we can write it in the ax plus by plus c, equals c as a standard linear equation. Okay, but so now, so definitely I have to highlight the only access that we can do to find our slope of any tangent line is to find either the dy dx, see what I'm saying now, or the dx dy right here. Okay, but I'm sure at this point any viewers, including me, is more comfortable with the dy dx, because it's just us. We've been driven so long into that path of seeing y as a function of x, so let it be. See, I'm not saying that our curve in this example, is a function y of t immediately, but I'm not saying that we see the graph. That's what I meant like that. But let's say if the graph there can be a function y in terms of x, then this is what we can do. And as I said, we didn't have to see the graph. But now let's say, think about if y is a function of x, right? Then we already learned earlier that, okay, dy dx, because this is the only way that gives us access to calculating the slope at any point, because any point on a curve in the end, any point on a curve is only represented by two values, x and y. Okay, so to find the slope of the tangent line, we need to find either, as I said earlier, either a dy dx or the dx dy. And here a lot of us, including me, are more comfortable with writing y as a function of x. So let's go that way. It doesn't hurt. You can also break out of the box and go with dx dy as well. It won't give you the wrong answers. Okay, but you got to be a little bit more careful. That's all. So now, the dy dx here is going to be, so just now I introduced that formula, but you can feel free to rederive the whole thing again. But so dy dx here was introduced earlier as dy dt over dx dt. Okay, so why do I have to bother bringing this up? Because here's the thing, we have to calculate dy dt, dy dx, to calculate our slope of tangent line. Because none of these, the dy dt and dx dt does not have a direct graphical understanding right on our curve. See, anywhere on our curve here, if you draw a tangent line, that tangent line here is just the slope of just y changing y over changing x, or you can see that as a changing x over changing y. Okay, but we don't see how the variable t can be represented graphically, part of the picture here. So that's why you can't use the dy dt or the dx dt to calculate the slope of the tangent line. We can only use these as part of a part of what's contribute into calculating this dy dx, but the dy dx is the one that directly gives you your answer. Okay, and that's what my point is. And so, and here sadly, our curve is not directly written as y in terms of f of x, and that's why we have to go through the route where we're gonna use the dy dt and dx dt together. Okay, so now isn't it obvious that our x of t is t cubed plus 2t, okay, and our y of t was t squared plus 7t. Okay, so now we can easily find that dx dt is 3t squared plus 2, and our dy dt will be easily 2t plus 7. Okay, and so now from that, now I'm going to use these to set up our calculation there. And so now for our dy dx, this is how we're setting it up. We don't have a direct work to find dy dx, so we have to go through the parametric rates right there. So dy dt is a 2t plus 7. I put that in the numerator. Okay, the dx dt is the 3t squared plus 2 that I put in the denominator. Okay, so this is going to be, so now once we had it set up, and as long as we have a value for t being given right here, we should be able to calculate at that instant t right here. Because now imagine again, a curve can be whatever, but every point here happens at a specific time instant. Okay, and so at which time instance will we have a curve like this? I mean, at say at this given time instance, what slope of our tangent line is that? And then at another time instance, what is the slope of our tangent line? Okay, and that's what it is. Okay, so just like the standard step, finding the slope of the tangent line, we got to get the dy dx right there. Okay, and I actually wrote this a little too soon. But so now the actual slope of the tangent line we're looking for now is, go ahead and our dy dx, but I'm going to substitute in t equals, because we are at the given time, t equals -1. This is what we have right there. Okay, and so in that way, t equals -1. So now I can go ahead and substitute t equals -1 into this dy dx expression right here, which is only in terms of t. So now we have 2 times -1 plus 7, okay, over 3 times -1 all squared, okay, plus 2. All right, and so now that gives me 5 in the numerator over 5, and that is 1. Okay, and that is 1. Okay, so now we know that our slope of the tangent line is 1. And so now we're still not done with question A yet. Question A is asking further that complete the equation of the tangent line. All right, and so now complete the equation of tangent line. We can write our equation of tangent line together with our previous understanding. Then equation of tangent line can be a y equals mtx plus b. But if we are going this route, we must obtain, we're going with this route if our derivative was a dy dx. Okay, and on another hand, because in the end an equation is only an equation, it could be a y in terms of x, or it could be an x in terms of y. So here I can also come up with big M, t is always for tangent, so big M y plus b right here. It's another slope slope intercept, but completely expressing x here as a function of y right here. We would go with this route if we calculated our slope here as a dx dy. But in our case here, I did not go that way. It's just a choice. Like I said, any one of these choices, and you already had that tool. After this video lesson is over, after this example problem is over, I highly recommend that you can also restart the entire problem and start out by finding the x dy and try to come up with your x right here. Your equation, same equation of tangent line, but expressing x as a function of y, and see how that will work for you. Okay, and so now since we had our our dy dx previously found being 1, and so now I am going to finish out my equation. So my equation of tangent line. So let me get on the other board to make use of my remaining space right here. So to find that, so now my tangent line is halfway done. It's going to be 1 times x, which is x plus b. All I need to know now is that we need to find out what our tangent point is. See, all the standard step for completing equation of tangent line now is here. So tangent point. We start out always by finding the dy dx, and doing that will get us the slope of our tangent line. And then after getting the slope of our tangent line, we're gonna have to find out where our tangent point is, where the tangent line meets with the curve. Okay, but now the curve here is completely expressed parametrically, completely parametric. And so that means here's how I find my tangent point. This is at t equals -1, at t equals -1. So I'm a little narrow space here, so let me write it on the other board. So at t equals -1, then this is what we have right here. X of -1. I'm talking about substituting times -1 into our x equation, our x parametric equation of the particle, of the object there. Okay, and so now we're looking at -1 all cube plus 2 times -1. Again, because x of t in general is t cube plus 2t. And so now it is going to give me -3. That's my x coordinates when t equals -1. Okay, and so y value is going to come out being y at -1. And so my equation here, my parametric equation, is a t squared, so -1 all squared plus 7 times t, which is now substituted by -1. Okay, because again, recall for yourself, y of t equals to t squared plus 7t. Okay, and so all that work here equals -6. And so that means our tangent point is at, now let me switch to the other board right there to just fill in what's missing. So our tangent point here, after so much calculation, it's at when t equals -1, our tangent point is at -3 comma -6. Okay, let me open a little side note here and mention now, if anyone happened to view this video at your level being a pre-calculus student, finding a point on the parametric curve when at a given t is also the same as the kind of problem where, hey, find the position of your particle, find the position on the curve at t equals such and such given. And so here if we use that point for in the purpose of our tangent point, but generally speaking, substituting a value for t, okay, substituting a value for t into our parametric equations will also give us the position of the points on the curve at that instance, t equals whatever given here. Okay, and so now, so back to what I'm having here at the instance t equals -1. On the curve we are at that point, but now since that point has the tangent line going through, so we now regard to that point as the tangent line. I mean as the tangent point. Okay, but simply this is a point, a position on that curve at that instant t equals -1. Okay, and so now let's finish out the problem. So now having the tangent points given, then our equation is very close to be completed. Okay, so now with our halfway found, y equals x plus b. Now tangent point is at -3, -6. Just a quick recall from that. So now I am just simply going to take y, substitute for y in the equation, and x value of the tangent point, substitute for the x value in the equation. Now we're looking at -6 equals -3 plus b right here. We're getting closer and closer. And then I noticed I should have used a lowercase letter b throughout the whole time, but it's okay. You should be able to understand that. And so our y-intercept now is going to be b equals -3 right there. So final equation of the tangent line, y equals x minus 3. X minus 3. Okay, so here's the thing. So one thing we have to note, our final equation of the tangent line is a Cartesian equation. Okay, Cartesian equation. That's one thing we realize. But here's the thing. It's just the way it is. A lot of time the problem itself, and look right back in the wording of our problem itself, it didn't even tell us complete the equation of a tangent line, but did not tell us the equation as a parametric equation in terms of t or a Cartesian equation. But behind the scenes, I mean, it means it's intended to be the Cartesian equation. Okay, you can, in our equation here, writing our equation as a function y in terms of x, it's just our choice, my choice, that I'm more comfortable, and I'm among those people who are more comfortable with treating y as a function in terms of x. But if you are among the group of people who are more comfortable with treating x as a function in terms of y, you can go the other way around by starting out with finding the x dy, as I have mentioned previously. Okay, but your equation at the end is again a Cartesian equation. Okay, so it's just an automatic responsibility that's being assumed anywhere worldwide when you're doing math. That when you come to finding equation of a tangent line, even though you're on a parametric curve, your equation in the end is still going to be expressed as a Cartesian equation. Okay, and so there you go. That's your equation of a tangent line. And so now that's our part A of the example. That's our part A of the example. All right. And so now let's look at part B of the example right here. Okay, so it's just part B, but it's supposed to draw out the exact same information. So those parametric equations remain the same here. Now we want to find the coordinates of the point. So the coordinates here in plural, it means the x and y coordinates value. Okay. So find the coordinates of the point on the curve where the tangent line is horizontal. Interesting problem. Interesting problem. Okay. We want to find the coordinates of the point on the curve where the tangent line is horizontal. Okay. So let me quickly do a sketch and to explain what exactly is the problem looking for. This problem, let's say again our parametric curve is just whichever curve. It can go crazy, looping around whatsoever, but there has to be some instances. There must be a few instances where the tangent line reach or becomes horizontal. Okay, maybe our curve starts here and go around this loop. And so at some instance, there must be some instance where our tangent line, see, here the tangent line was not horizontal and it was way vertical, and here it's horizontal, and here it's horizontal, and in a different instance. Okay, so the idea now is that we want to find out at which instance. There could be more than one instance. Okay, but at at which instances on this parametric curve here that our tangent line will become horizontal. But now the bigger importance here, I mean the bigger thing you need to understand, the larger impact you got to understand is that being a horizontal tangent, the bigger clue, that's what I meant earlier to say, the bigger clue for you to recognize is that being a horizontal tangent line means the slope of the tangent line here has to equal to 0. And the slope of this tangent line here has to equal to 0. That's the one important key right there for us to pull through with the problem. Okay, and so now here's how I'm getting to it. So our equations are, let me rewrite it down, t cubed plus 2t for x, and y is of t is t squared plus 7t. Okay, and we also found the x dt and dy dt previously in part A right here. Let me retrieve all that. So the x dt was 3t squared plus 2. Okay, and the dy dt here we found previously was to be 2t plus 7. Okay, so looking for a horizontal tangent line means slope of the tangent line at those instances must be 0, mt equals 0. But mt equals 0 means it means we're also looking for dy dx. We want dy dx. That's our goal right here. We want dy dx to equal 0 because dy dx is our slope of the tangent line. Okay, but now see, thankfully my other board is still there, but and not erased yet. This was our dy dx general formula for the slope of the tangent line at any time instant t. So it's a 2t plus 7 over 3t squared plus 2. See, the dy dt over the dx dt here. Okay, so now we can go ahead and recall that and put it back here on this board. So that means the dy dx here, I can now go ahead and it's 2t plus 7 over 3t squared plus 2. We want this dy dx here, completely in terms of t, is to equal 0. And now we're going to solve this equation. We're going to solve this equation here for t. Okay, so the equation at first sight looks complicated, but it won't be that bad actually, because first of all it's only one variable and it's equal 0 on the right hand side here. And think about this, the t squared itself in the denominator is always non-zero, greater than or equal to 0. That's what I meant by, non-negative, greater than or equal to 0. And so similar 3t squared will be the same. Multiplying a positive number to both sides of an inequality won't change it. And so 3t squared will consequently be greater than or equal to 0 as well. But 3t squared add 2, because that's what our denominator here, must be greater than or equal to 2. But greater than or equal to 2 means it has to be positive. The quantity in the denominator here be positive. And the further impact, it cannot be equal 0 in the denominator. So that means we can solve this algebraically, and it's back to the algebra again. I'm going to multiply both sides by the 3t squared plus 2 here. So that gives me, okay, so let me clear out my other space right there to give myself some space to work with. All right, so I just reconstructed that equation here. So back to what I was halfway arguing earlier. So now the 3t squared, you can pause the video to think about what I'm saying, but now 3t squared must always be a positive quantity, not even equal to 0. It can't equal 0. And so now we are safe to multiply both sides of this equation here. It's just a technique for solving equations. It's really nothing calculus. 3t squared plus 2, multiplying both sides. Okay, 3t squared plus 2. And now that gives me 2t plus 7 equals 0. Okay, and so now this equation here all of a sudden is a lot simpler for us. We can just simply solve for that by subtracting t to the other side and dividing both sides by 2. Our final t value is a negative 7 over 2. Okay, and we only found one answer. That means, what have we found here? We found that no matter how the curve will go crazy and bends, but maybe I'm drawing the wrong curve because it seems like on this picture I'm drawing there are too many instances where the t here is where the tangent line is horizontal, but for the curve we actually doing, which is probably not this unlikely to be this curve I drew over here, but the instance where the curve becomes horizontal is the instance where it's negative when t equals negative 7 over 2. That's what I'm trying to explain right there. Okay. So, but that's actually not our final answer yet. It's just the time instance where our tangent. It's just a time instant where our tangent line reach horizontal tangent line. But the problem is actually looking for the coordinates of the points. Okay, the coordinates of the points. And so now, but we have made for ourselves a huge victory here, because now once we have found that the tangent line will become horizontal at this time instance, negative 7 over 2, then this is what we can do with this value, negative 7 over 2 for t. Our equation, x coordinates is t cubed plus 2t. And so now we are ready at t equals negative 7/2, where it's the time instant when we reach horizontal tangent. Then the x coordinates now must be x value at negative 7/2. Okay, so now we just go ahead and plug it in. So negative 7/2 cube plus 2 times a negative 7/2. Okay, and I'll save all that calculation for the last step. And the same with y value. Once we've had a time, when time equals negative 7/2 right here, then y of t, well, recall for yourself, it's t squared plus 7t. So that means our y coordinates here for that point where the tangent becomes become horizontal, that's y at negative 7/2. And that now gives me negative 7/2 all square plus 7 times negative 7/2. Okay, and then now I'm going to quickly step away for a quick calculation, and for viewers, you are more than welcome to come up with your own answer as well. Okay. All right, so my calculation shows the coordinates are x equals negative 399 over 8, and y equals negative 49 over 4. And that's our coordinates that we're looking for. This is the coordinates responsible, the coordinates that's driven by time right there. But this is the coordinates where we reach a horizontal tangent. But the time there, the time it hits to this coordinates is this. And so, as a generality of this kind of problem, maybe when you might be doing a problem that's very similar, but it's asking for find the coordinates of the point on the curve where the tangent line is at slope. So instead of being directly horizontal, when the tangent line is at a given slope, maybe slope 5 or something like that. Okay, so the point now is that you have some clue that tells you about some information about your given slope. So here our slope is given to be 0 because the clue here was the horizontal tangent. But maybe some other problem, it could be, find the coordinates where the tangent line is at, slope 5 or slope 24 or slope -10 or something like that. Then you use that given slope value here, and then you solve for your equation. And believe me, see, I did this problem here, solving the equation simply by just manipulating some simple algebra here. It shouldn't be too much to understand. And so most of the time, you will run into equations similar to this with simple algebra that you can just solve. But the big key step here is to solve the value for t, because we want to find out at which time instance responsible for reaching the slope of the tangent line being in that designated specific given value. Okay, and once you can find out at which time instance we reach that designated tangent line with slope as specified, then we can go ahead and use that time value that we calculated, substitute that into our parametric pairs of equation, and there we come up with the pair of coordinates value. Okay.